Hi all, good evening. In today's lecture, we'll see about Z transforms and discrete linear time invariant systems. I am Dr. Kishore here. So we know that for a discrete time linear time invariant system with impulse response h of n, the output y of n of the system to the complex exponential input of the form z power n is y of n equal to transformation of z power n, which is equal to h of z into z power n, where h of z equal to summation n equal to minus into plus infinity h of n z power minus n. Now for a general discrete time signal x of n, the z transform x of z is defined as x of z equal to summation n equal to minus into plus infinity x of n z power minus n. So this z we call it as a complex value expressed in the polar form z equal to r into e power I omega, where r is the magnitude of z and omega is the angle of z. Now let us recollect these concepts of what we have done. So we call when summation runs from n equal to minus into plus infinity with x of n into z power minus n, we call this x of z as a bilateral z transform or two-sided z transform. Suppose when n runs from 0 to infinity, then we call that as a unilateral z transform or one-sided z transform. So the bilateral and unilateral z transform are equivalent only if x of n equal to 0 for n less than 0, and x of n and capital X of z are said to form z transforms pair denoted as x of n to x of z or x of z to x of n. So this one we call it as z transform pair, right? Now let us discuss about region of convergence. So what is region of convergence? The range of values of the complex variable z for which the z transform converges is called the region of convergence. So what does it mean? Whenever we take all the values of the sequence and when you add it up, that when it converges to a point, we call that as a convergent sequence, and that convergent sequence will have a region, we call that as a region of convergence. So again, when we want to speak about that more, let us consider this example. Consider the sequence x of n equal to a power n into u of n, where a is a real number. Then the z transform of x of n is given by x of z equal to summation n equal to minus into plus infinity x of n into z power minus n. Now we are going to just substitute x of n as a power n into u of n. Now what about this u of n? Now this u of n will take values 1 when n runs from 0 to infinity, and when it is lesser than 0, for those numbers, negative numbers, this will take 0. So this one, this minus into plus infinity, now that will be converted to 0 to infinity. The reason is u of n is going to take the value 1 for n equal to 0 to infinity. So this one I'm not writing it here, and I'm just clubbing this two together, a power n to z power minus n, which is a z inverse power by n. Now when you take the absolute value of this, that will be less than infinity, we call that as absolutely summable. So whenever this x of it is going to converge, then this condition should get satisfied. So we are just going to check it out. We take x of z equal to summation n equal to 0 to infinity a z power minus 1 power n. Now this will be written as 1 by 1 minus a z inverse. How do we write that? We have these rules, you can see it here. Summation n equal to 0 to infinity alpha power n, which is nothing but 1 by 1 minus alpha. Summation n equal to 1 to infinity alpha power n, which is alpha by 1 minus alpha. And summation n equal to k to infinity alpha power n could be written as alpha power k by 1 minus alpha. So these three rules you need to understand. So by rule number 1, you can see here, instead of alpha you have a z power minus 1, so it becomes 1 by 1 minus e z power minus 1. And the region of convergence for this, actually we have this formula. Whenever you have this quantity should be less than 1. So when this is going to be less than 1, then mod z will be greater than mod a. So how do we get that? Let us see here. See, when I say a z inverse modulus value is less than 1, this will be a by z absolute value is less than 1, then that becomes modulus e less than modulus z. Now this will imply mod z is greater than mod e. So this is the region of convergence which we have noted here. So I hope you understood these steps very clearly, right? So that's how we get this region of convergence here. So we got mod z greater than mod e, right? Now this is a right-sided sequence. We took e power n into u of n and we proved the we got the answer for is a transform which is going to be z by z minus e or 1 minus e z inverse. We can write even like this also, but the region of convergence is mod z greater than mod e, right? Now let us get into the next example where we are going to see the left-sided signal x of n equal to minus e power n to u of minus n minus 1 where e is real number. So the z transform of x of n is given as x of z equal to summation equal to minus n to plus n to x of n into z power minus n. Now this one x of n we are writing it as minus e power n into u of minus 1 into z power minus n. Now actually this u of minus n minus 1 will be 1 for all the values which is lesser than 0. That means when you take minus 1 minus 2 etc minus infinity, this value become 1, and remaining places when it reaches 0 and above 0, this value becomes 0. So I'm just gonna write this minus has been taken here out and I'm writing a power n into z power minus n, but here the range for n is going to be changed, n equal to minus n to minus 1, because from this range you have u of minus n minus 1 to be 1. So I hope this concept is clear. Now you will be left out with a power n to z power minus n here. Now again I'm just going to replace this n value as minus n. So what will happen here? Minus n becomes minus infinity, therefore n becomes infinity. And when you take this value n minus n value to be minus 1, what happens to this value? This value becomes plus 1. So I am writing this n equal to minus n to plus infinity after replacing minus n instead of n. This becomes n equal to 1 to infinity a power, this n becomes minus n, this n becomes plus n. Why? Because we replace n as minus n. Now when you see, you take this a power minus 1 into z whole raised to the power n, which will be actually this is summation n equal to 1 to infinity a power minus 1 z power n. We can skip this step and write this directly. So how do I write? By using this rule here. Actually here we have this rule, and again we also have this n equal to 1 to infinity alpha power n, which is alpha by 1 minus alpha. So again I'm writing all these rules. So what we have written here, I'm writing it here again just to make you understand. So here n is running from 1 to infinity, so we're going to use this rule, alpha by 1 minus alpha. Alpha is nothing but a power minus 1 into z, so it is a power minus 1 into z by 1 minus a power minus 1 into z with negative in front. So when you just take this a power minus 1 as 1 by e, or just multiply with a in the numerator and denominator, you will be getting z by z minus e. Now you can very well see this left-sided signal which has also got the z transform to be z by z minus e, as well as the right side signal also got the z transform as z by z minus e. So both these signals have the same z transform, but to look on to the region of convergence, what happens here is you can closely watch here this quantity. Okay, when you expand, it will be in this form, right? So when you have this form, the denominator part again, you take this absolute value should be less than 1. So because it should converge to a point. So when you take that quantity less than 1, now from this we may get like, you will have like this, right? Let me write it here. A inverse is that this can be written as z by e. Now this is less than 1, right? So mod z will be less than mod e. So this is how you get the region of convergence here. So I hope this step is very clear for you. So what happens to the region of convergence? The region of convergence is mod z less than mod e in the case of left-sided signal. but whereas in the right side the signal is small z greater than mod a. And to note very clearly, the z transform for both the signals are same. So for both right and left side signals, its x of z is a rational function of z, and the roots of the numerator polynomial we call it as zeros, and the roots of the denominator polynomial we call it as poles. So to note this z transform, the numerator part you can see here, I'm just taking this as a transform. So when you equate it to 0, numerator we call it as 0, denominator when you equate it to 0, this is x z equal to e, which is the pole. So that's what I told here. Z equal to 0 is a 0, and z equal to e is a simple pole, because you have the power of this z minus e to be 1. Note that the z transform of right side and left side signals explained above are the same, but their ROCs are not same, as I told you. Now let us come to this problem. A discrete time causal system has a transfer function h of z equal to 1 minus z power minus 1 by 1 minus 0.2 z inverse minus 0.15 z power minus 2. Now we are going to determine the difference equation of the system, and we are going to draw the pole zero diagram, as well as we are going to find the impulse response of the system. So let us take this transfer function h of z equal to this question. Now the numerator we will consider as y of z, denominator we will consider as x of z, so it is y of z by x of z. Now you just cross multiply this y of z into this quantity equal to x of z into this quantity. So I just cross multiplied. Now I'm going to apply the time shifting property. When x of n is x of z is a transform, when you take it's going to be x of z, then x of n minus n naught can be written as z power minus n naught into x of z. So this property we call it as time shifting property. Now when you see this y of z multiplied with this 1 and these quantities, y of z is considered as y of k, I mean here it is y of k, okay. So you can see in this way. So x of z is x of n, so y of z is y of k, and z power minus 1 into y of z, z power minus n naught into x of z is x of n minus n naught. So this will become, instead of n naught you have 1, so it is y of k minus 1 into minus 0.2, so you get this quantity. Similarly, z power minus 2 into y of z becomes y of k minus 2 into minus 0.15, and x of z becomes x of k, and z power minus 1 into x of z becomes x of k minus 1 by using time shifting property. So this is completely by using the time shifting property we are getting from this term to this, I mean this expression, so which is called the difference equation of the system. Now before finding before getting into pole zero diagram, let us find the impulse response of the system. So how do we find that? So you just take this function h of z. Now the denominator part, I am just replacing it 0.2 as 1 by 5, or 2 by 10. 2 by 10 becomes 1 by 5 otherwise. 15 by 100 becomes 3 by 20 here, okay. So in that way we will write. Now we are going to factorize this in this way, but how do we do that? We'll take this term and we will just see the LCM of this 20 and 5, which is going to be 20. Multiply the 20 with this term, okay. I have multiplied. Now 20 into 1 is 20, 20 into 1 by 5 is 4, so it is minus 4 z inverse, and 20 into minus 3 by 20 is minus 3 z power minus 2. So now this term you multiply 20 with minus 3, that is minus 60, and you can just take two factors of minus 60, which is minus 10 and 6. Why we are taking this numbers? Because when you add minus 10 plus 6, that will give you minus 4, I mean this term, and when you multiply this minus 10 into 6, that will be minus 60. So what I'm gonna do, I'll take these numbers. So minus 4, I'm writing it as minus 10 plus 6. So now these two terms you can take 10 outside, so you will have 2 here and minus z inverse here. From these two last two terms you can take 3 z power minus 1, so you have 2 here and minus z power minus 1 here. Again from these two terms you can pull out 2 minus z inverse, so you get 10 plus 3 z inverse into 2 minus z inverse. Now from these two terms you can see this 10 and 20, 2, I'm going to take it out, that will become 20. So in this place you will have 1 plus 3 by 10 z inverse. In this place you have 1 minus 1 by 2 z inverse. So what happened here? 10 into 22 becomes 20. So we see 20 into this term equal to 20 into this term. So we can cancel this 20 and 20, leaving out. Instead of this we will write 1 plus 3 by 10 z inverse to 1 minus 1 by 2 z inverse. I wrote it here. Okay, you can see these two steps. Now, why do I go with this? Because I want to make it into partial fraction method, and I want to just decompose this. So what I'm gonna do, I'll just write this two factors here, so which is taken to be a by this term plus b by the second term. Now when can you use this? Whenever you see this power of z, not z inverse. When you multiply with z, you will get z, and here you multiply by z square, you will get z square as the highest power. Here you will have z, here you will have z inverse z square. So the power of z in the numerator should be lesser than the power of z in the denominator to apply this partial fraction method, right? So we will just do that. So what I'm gonna do, I just use my cover up method to do this process. So let me take this quantity in the denominator 1 plus 3 by 10. I'll just show you here. So 1 plus 3 by 10 z inverse is equal to 0, which will give me 3 by 10 z inverse equal to minus 1, or z inverse equal to minus 10 by 3. So that I'm going to substitute it here. You can see I will substitute, where if I substitute here, this quantity becomes 0. That's why we'll cover this term and we'll substitute only in this place. This z inverse to be minus 10 by 3. This z inverse place is minus 10 by 3. So we'll get 1 plus 10 over 3 by 1 plus 5 over 3, which becomes 13 over 8. So the answer for A is 13 over 8. Right. Now, what about z inverse equal to 2? How do we get that? Go with B. Take this term. Now here you will see here in this place 1 minus half z inverse equal to 0. Okay, I will even write in this way also. Both z is going to be same. Okay, do not confuse. So z inverse value is going to be 2. Now I'm substituting z inverse equal to 2, but where should I substitute? If I substitute here, it becomes 0. So I will cover this and I will substitute in these two places. Is z inverse value to be 2 here, so here also 2. So you get 1 minus 2 by 1 plus 6 by 10, which is 1 minus 2 by 1 plus 3 by 5, which is equal to minus 1 by 8 by 5, which is minus 5 by 8. So now this b value is minus 5 by 8. Now we are going to substitute a and b values here. So after doing so, what happened here is I just multiply with an z in the numerator and denominator for both these terms. So what will happen? 13 by 8 z by z plus 3 by 10 minus 5 by 8 z by z minus 1 by 2. Now if you take z transform, this is h of z, right? So when you want to find the impulse response h of n, take this is z transform, I mean z inverse. If you want to take for h of z, that will be z inverse of this term. So you take this 13 by 8 out, so z inverse of z by z plus 3 by 10 minus 5 by 8 into z inverse of z by z minus 1 by 2. So I hope you get this concept, right? So this formula z by z minus e, what is the formula for z inverse of z by z minus e? So the formula is a power n, and here it is into u of n, because it is the unit step function. So we can just write in this way. So this is the formula you will get. So 13 by 8 into minus 3 by 10 power n into u of n minus 5 by 8 into 1 by 2 power n to u of n. So this will be your impulse response. Okay. Now to get into the pole 0 diagram, you take this h of z in this way. Now what I have done here is I just multiplied with an z here. Here I multiplied with like 2z for I mean otherwise you multiplied with z square, right? You can multiply with z square here. Here also you multiply with z square. So what will happen here? Z square minus z, that will be z into z minus 1. Here for z square you can give 1 z to this place and 1 z to this place. Multiply, you get z plus 3 by 10 into z minus 1 by 2. So you will have this form. So why should I bring this form? Because I told you very clearly the numerator part, when you equate it to 0, that is going to be zeros. So z equal to 0 and z minus 1 0, which is z equal to 1. These are the zeros of h of z. And when you equate the denominator to 0, here you get z equal to minus 3 by 10, which is minus 0.3, and z equal to half, which is 0.5. These are the poles of h of z. Now what is the region of convergence here is, see, actually I told you both these parts you can see here, you have mod z is greater than 3 by 10 as well as mod z is greater than 1 by 2. So when you plot this, you can see very well zero point 0.5 is superior than 0.3. So obviously from 0.3 it goes outside, and from 0.5 again it goes outside, but the intersection of both, you can see here, the intersection of this mod z greater than 3 by 10 mod z greater than 1 by 2, which will leave mod z greater than 1 by 2. You can see this picture. So this is the pole 0 diagram, where you can see two poles, one is minus 0.3 and one is 0.5, and mod z, and you can see the zeros, z equal to 0 and z equal to 1 here, which is the blue dots. Now mod z greater than 0.3 is nothing but from this place we are just marking all, you can see this red lines, okay, all the red lines. But mod z greater than 0.5, which will be, you can see this blue lines, I just marked this side, right? So the intersection of this blue lines and red lines, where are they? It is just outside this concentric circle, I mean all these places, right? So this is your region of convergence actually. So you can very well shade this part, and you can tell this is the region of convergence. So this is the pole 0 diagram. So I hope you are clear with this problem, and with this we will end up our lecture, and we will see a lot of properties of region of convergence of Z transforms in the next video. Thank you.